why hasn't extraterrestrial life contacted us yet is the core question of the Fermi Paradox. In short, the observable universe contains so many millions of billions of stars and planets that the chances of intelligent life arising elsewhere, and probably many places elsewhere, seems almost inevitable. And yet, we haven't heard from any aliens. One possible explanation is that we're overlooking quantum mechanics. Here's the thing, to communicate long distances in space, it may be that you need to be using quantum communication. A fundamental problem with interstellar communication is the speed of light. The distances between stars are just so big and light takes so long to get there, you have to be really efficient with your communication. You don't want to wait a decade to hear back, "Sorry, you cut out for a moment, can you say that again?" And it turns out that quantum communication, where you send photons that are entangled or in a carefully superimposed quantum state, quantum communication can be incredibly more information dense than non-quantum communication. In one protocol, any number of quantum bits can be used to transmit twice as many non-quantum bits, and in another setup, it takes exponentially more non-quantum bits than quantum bits to transmit a particular type of information, though both of these quantum efficiency gains have caveats that we'll explain later. But regardless, quantum communication being more efficient doesn't on its own explain Fermi's "where are all the aliens" paradox. Quantum communication, it turns out, has some very particular requirements, and it's those that might help solve the Fermi paradox. Specifically, to send quantum information to someone else, you can't just broadcast a signal out in all directions like you can with radio waves or whatever. The laws of physics require the person receiving the quantum information to get over 50% of the photons you send in order to reconstruct the info. So instead of broadcasting a quantum signal, you have to focus it. The equation for this tells us that the size of the transmitting and receiving telescopes must be really big. Exactly how big depends on how far you're sending the message and what wavelength of light you're using. And the 50% receipt requirement means you have to send a quantum signal using photons with wavelengths that'll pass undisrupted both through the Earth's atmosphere and across interstellar space, rather than getting scattered off of interstellar dust or whatever. And the numbers work out such that if you want to do quantum communication with Alpha Centauri, the nearest star system to us, you need a telescope around 100 kilometers in size, and a bigger one for more distant locations. And this is not like the Very Large Array where they have radio dishes really far apart to simulate having a large telescope. In this case, you actually have to build the whole telescope, because you have to get more than 50% of the photons. Interstellar quantum communication is a hard thing to do. Perhaps now you can start to see how this explains the Fermi paradox. Suppose that widespread alien civilizations are using interstellar quantum communication with huge oversized telescopes, and for their quantum communications to work, each transmission has to get the majority of the transmitted photons into the receiving telescope, which means that very few would stray off by happenstance to be detected by our undersized telescopes. And because we wouldn't receive more than 50% of the photons from a transmission, both because we don't have a big enough telescope and the signal wouldn't be pointed at us anyway, it wouldn't be possible to understand any of the information we received. Basically, aliens communicating quantumly could be sending messages whizzing past us all the time, and we wouldn't know. Plus, any aliens that had telescopes powerful enough for quantum communication with us would also consequently have telescopes good enough to see that we don't have telescopes powerful enough for quantum communication. So they would know that sending us a message is futile, and therefore perhaps wouldn't bother. In summary, our theoretical and experimental understanding of quantum information suggests that aliens might be likely to use quantum interstellar communication rather than non-quantum communication, which means aliens would be sending narrowcast messages that would mostly pass us, and even if we could intercept them, we wouldn't have the capacity to intercept enough to receive the message, and therefore we would expect not to hear anything. And that's the Fermi paradox solved. Kind of. There are still some open questions, like if aliens wanted to communicate with us and could tell we couldn't receive a quantum message, why wouldn't they just send us a regular signal like with radio waves or something? And also, if aliens had traveled through the galaxy to set up a network of giant telescopes, couldn't they just come visit? But answering those is beyond the scope of this video. Whether you're an alien learning to build an interstellar quantum communication network, or simply a human like me wanting to excel at learning science, I recommend Brilliant, this video's sponsor. Brilliant allows you to learn by doing, utilizing step-by-step interactive lessons that guide you to understand from first principles, such as their scientific thinking course, which teaches logical and scientific problem-solving through the lens of everyday physics and engineering puzzles. Brilliant makes it easy for anyone, whether you're 10 or 110, to learn in a more fun and effective way than just watching videos. To sign up for Brilliant for free and get 30 days of full access to all of their courses, go to brilliant.org/minutephysics, or scan the QR code on screen, or click on the link in the description. You'll also get 20% off an annual premium subscription for all of Brilliant's content. Again, that's brilliant.org/minutephysics, and thanks to Brilliant for their support. Okay, now for the caveats. The protocol called super dense quantum coding allows you to send 2 non-quantum bits of information from each quantum bit you send, which seems like a 2x speedup. Except it requires the receiver to already be in possession of an entangled quantum bit from the sender in order to receive the message. So you'd either have to bring a big supply of pre-entangled quantum bits with you when you built the receiving telescope, or the sender would still have to send 2 quantum bits to transmit 2 non-quantum bits, in which case they could just send the non-quantum ones. The other procedure, called the hidden matching problem, which requires exponentially more non-quantum bits to be sent than quantum ones, this procedure also requires the receiver to already be in possession of some information, and it's not clear exactly how it would be turned into a general communication protocol. But it has been proven that this procedure is exponentially faster when you communicate quantumly than non-quantumly.